How you doing? I'm Mr. Rose, and today we're going to continue to talk about electrostatics. Now, in the problem you see in front of you, you can see, that we're talking about a thin rod that's bent into a semicircular shape. They talk about linear charge density. We're looking for an electric field. We're looking for units of whatever that constant is, K. So I'd like you to take a minute, read through the problem, write down any important information that we need, and we're going to move forward. Okay, so now that you've written down all the important information, let's go to a clean sheet of paper and let's begin. So again, the problem told us we have this semicircular rod, and the semicircular rod has a linear charge density. Now I remember right away, linear charge density is brought to us by the Greek letter lambda. And if I remember specifically, lambda, or linear charge density, means a charge per unit length. So essentially, we're in a coulomb per meter. And they told us that the semicircular rod has a linear charge density, I'm just looking at the problem down here, a linear charge density of negative k theta. So I'm going to define lambda as negative k times theta. Given information. Beautiful. Now assume k is a constant. Awesome. Part A, what are the units for k? This is a very standard question, and it should not be that hard to apply some dimension analysis. Now we know that lambda is equal to a coulomb per meter, which means when I'm done with this, I need to be in a coulomb per meter. And I should also know that theta is going to be in either radians or in degrees. Now, I know that I want this in radians, so I'm going to use radians. Just going to cross that right out. If for some reason you chose degrees, you'll see when we do our problem why we chose radians to begin with. But if for some reason you chose degrees, our units would cancel out the same no matter what. So I need lambda to be in a coulomb per meter, which means I need K to be in a coulomb per meter. So K must be in some coulomb per meter. So I'm going to end with that, but I've got to get rid of these radians. So it's going to be a coulomb per meter times a rad. Then that radian will cancel with that radian, left with coulombs per meter, and that is beautiful. Dimension analysis for K. K has to be a coulomb per meter. I just want to extend that so it looks better. K, there we go. It has to be a coulomb divided by a meter times radian. So that's part A. Part B now, derive an expression for an electric field at the center of the semicircle. So that might be a little bit more tricky. And to do that, I'm going to start with, you guessed it, I'm going to draw a picture. So bear with me here. I'm going to make that my center. That might not be the best picture, but here is my semicircular ring. This is my spot at the center where I'm trying to find the electric field. And what we're going to do is we're going to remember, how do I find an electric field? Well, if this is uniformly charged, and it was uniformly charged with a negative charge, it was uniformly, if this is a charged ring, and it actually doesn't matter if it's a uniformly distributed charge or not, but the electric field at this point is going to come from every little piece of this rod. So I'm going to define a piece of that rod right there. And I'm going to define that with a length. What length am I going to define that? I'm going to define this as a length ds, like an arc length, right? So that length right there is ds, and where's that length coming from? Well, that's going to come from the fact that I've got this sweeping theta, that is drawn pretty terribly, but this sweeping theta, which I'll represent with this angle, theta, was given to us. So at every different point, this section, well, the section there, and then 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 there, are all going to add up to my electric field, as we can see. So I know that this ds also, inside of that ds, has a very small I'm going to write it right here. Every ds has some small dq, right? Because my whole length s would have a whole charge q. Well, how is that going to be helpful to us? Well, let's go back to review the stuff that we know. What we just did. Lambda, by definition, is a charge per unit length, which means, again, lambda, charge per unit length, which means this dq that I just defined, I'll put in a different color. This, sorry, I'm going to say that differently. Instead of saying this dq, I'm going to say if this entire thing, lambda, has a charge per unit length, that means I can set a proportion, right? Proportionally, I can say that lambda is also a small dq divided by a small ds. There we go. I like that better. Just so we're staying in the same exact fashion. So this is a charge per unit length, small charge per unit small length, and then I can start to rearrange things. I can say, all right, well, what exactly is that charge? I know, obviously, that charge dq is going to be equal to a lambda times a ds. All right, well, what are the things that I know about these things already? Like, what stuff do I already know? I know I was given lambda. So I know lambda, by definition, is equal to a negative k theta. And if I recall arc length, yeah, I told you there was a reason why we were using radians. If I recall arc length, I know by definition ds is equal to my radius times a d theta. So I'm going to plug in for ds, and now I have dq by definition is equal to negative k times theta times r d theta. Hey, I think that's going to be a useful thing to know. I'm going to write that sucker down right there. And we're still not done just pulling this problem apart. I'm spending a lot of time analyzing this such that we can do the actual calculus and the actual physics a lot easier. This is kind of physics by understanding as opposed to brute force. Well, I'm going to examine this one spot just because it'll make it easy for me. There's my one spot at the center of the circle, and I'm going to draw free body diagram. You know I love my free body diagrams. I know there is an electric field that I'm labeling DE specific to that spot DS. So I tried to mirror them in the same exact way. DE is going that way. Now, I also know that I can break that into components. I can say I've got a DE in the X direction, and I've got my very small electric field in the Y direction. Well, because I'm going to start to make these symmetrical arguments, I want you to think, wait a second. If this spot looks exactly like that, then the exact opposite side, that's what I tried to represent there, would look, I'm just going to do this whole one in pencil, just like that, where I would have an electric field in the Y direction there, and I would have another electric field in the X direction. So it looks like from this spot, from A, I'll just call it from 0 to A and 0 to negative A. I made those two things up. But that spot, and then its exact mirror on the other side, would have Y field, an electric field in the Y direction that cancels itself out, and an electric field in the X direction that is twice as big. Well, that's really important because I can then say from inspection, or say I say from inspection due to symmetry. Oh, that's good. My electric field in the Y direction, the sum of the electric field in the Y direction is 0 newtons per coulomb, which means the only thing I need to deal with here is the electric field in the X direction. I'm just making this easier and easier and easier. Let's get even easier. Here I have a whole semicircle. Well, I have got some negative semicircle, I've got some positive semicircle, but I just learned that everything on the bottom is identical to everything on the top. In the x direction, they're additive. So instead of going from negative pi over 2 to pi over 2, I can go from 0 to pi over 2, and then when I'm done, multiply the whole thing by 2. So that's where we're going to go with this. We're using a bunch of stuff that we know to just make this problem easier and easier and easier. So just go to a clean sheet of paper. I'm going to say I know the electric field in the x direction. So I'm first going to talk about, again, just this portion that I was talking about on the top half, the electric field in the x direction. I'm going to sum up all those things is going to be equal to the antiderivative of a very small electric field times the cosine of theta. Whoa, 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 why am I pulling this cosine of theta out? Go back. Remember, here's my theta. Look in the x direction. So it is my dE cosine theta. That's where that's coming from. But I just told you this is only the top half. And I'm going to do this all in one sweeping step, which means my electric field in the x direction is equal to 2 times the antiderivative of dE in the x direction times the cosine of theta. And I'm done. Wait a second, I'm not done. dE and theta, those things don't match. I know dE changes with respect to theta, so I need to examine my very small electric field such that I can sum it up and get a very big electric field. All right. Well, let's recall. Electric field is equal to 1 over 4 pi epsilon naught times Q over R squared. Perfect. Now we know that 1 over 4 pi epsilon naught can be simplified as K, the electrostatic constant. I'm keeping it with the permittivity constant for 2 reasons. Number 1, I just do it out of habit. Number 2, the problem gave us something with a constant K or a kappa. So I don't want to mess that up with my wonderful handwriting. So if I put those 2 things together, I may later on by mistake cancel them out. I don't want to do that. So I'm going to leave it as 1 over 4 pi epsilon naught. I'm then going to plug that into here. Well, wait a second. That's a whole Q. Since it's a very small one, that's got to be a dQ. Right? So my electric field is Q over R squared. My dE is going to be dQ. That very small charge from that very small spot. Beautiful. So my electric field, actually it's not even the x direction. My whole electric field, because we know all the y's cancel out, are 2 times the antiderivative of 1 over 4 pi epsilon 0. Instead of Q, it's a small dQ divided by, and because I used the capital R earlier, I'm going to say capital R squared times cosine of theta. Hey, and this looks like an indefinite integral. I know I'm going from 0 to pi over 2. So I'm going to plug that in there now. And again, it looks like I'm getting further and further away because now I have a dQ and a theta, and I know those 2 things don't work together either. So I'm going to go back again to things that I've already decided. My very small charge is in relationship to theta. Beautiful. Last substitution here. Electric field, 2 times the antiderivative of 0 to pi over 2 of 1 over 4 pi epsilon 0. I'm subbing in for my dQ, negative k theta, r d theta. So times negative k times theta times an r d theta divided by my r squared. That whole thing is times cosine of theta. And now we can see I've got a bunch of constants. I've got a d theta and d theta, so now I'm integrating about the same thing. That's always helpful. To make this a little easier now, let's start pulling out all our constants. My electric field is equal to, keeping that 2 I'm going to pull out the 1 over 4 pi epsilon 0. I'm going to pull out my negative k. I'm going to pull out my r on the top, my r squared on the bottom. Obviously, you know you're going to simplify that. And I'm going to be left with the antiderivative of 0 to pi over 2 of cosine theta d theta. Oh, I dropped the theta. There we go. Theta, cosine theta d theta. And now, hopefully, you recognize this as something that we've also done in the past. You should recognize this as an integration by parts. So if you remember how to do this, feel free to fast forward to the next step. I'm just going to give a quick review of integration by parts. So integration by parts is kind of similar to U substitution, right? Integration by parts, let's write what I have. I was given the antiderivative of theta cosine theta d theta. Now, I know this is integration by parts because it's in the form of u dv. What do I mean by u dv? Well, I'm going to look at this in the form of a u dv antiderivative. So I'm going to look at this, and just like u substitution, I need to set up what u is, what v is, what du is, and what dv is. So how do I do that? Well, looking at this, I know u is equal to my theta. Well, that's simple, because if u is equal to theta, du must be equal to d theta. Well, that's easy. Remember, antiderivatives are undoing derivatives. So this is undoing, that's why this is a derivative, undoing that dv, which means the dv in this case has to be cosine theta. Which means my v, what is the antiderivative of cosine theta? Sine theta. Right? Derivative of sine theta, cosine theta. Derivative of cosine theta, negative sine theta. So don't mess those guys up. Now that I have this, I'm in the form of antiderivative of u dv. Well, u substitution. Integration by parts means this antiderivative of u dv simplifies or expands, whatever the right word is, u times v minus the antiderivative of v du. All right, well, now substitute things in. This just makes it, oh, there we go. This makes it a little bit easier. U happens to be theta. V happens to be sine theta. Perfect. So uv, theta sine theta, minus antiderivative of v again, sine theta, du, d theta. Okay, so I'm left with theta sine theta minus the antiderivative of sine, negative cosine theta. Negative times negative is a positive. I'm going to flip those guys around, so I'm going to be left with a cosine theta plus theta sine theta. So here we go. We started with my antiderivative, theta cosine theta. In this form, it is an integration by parts. I set up my integration by parts. I know the antiderivative of theta cosine theta d theta comes out to cosine theta plus theta sine theta. So now I'm going to take that and plug it back into the beginning of my equation. So I have my electric field is equal to all of those constants I pulled out. I'm going to simplify on the fly. I've got 2 over 4 pi, which is going to be 2 over 4 pi, which is going to be 1 over 2. My K stays, my R is gone. So I have a K divided by 2 pi epsilon 0, R on the top is gone, over R negative K, because I pulled out that negative before, times what I just got up here, which is cosine theta plus theta sine theta. I believe that is all correct. I'm going to integrate that, or I integrated that from 0 to pi over 2. Whew. From here, it should be a trivial substitution. I guess I can just keep going through it because I'm almost done. We should get my electric field is equal to and there is my electric field. Negative K over 2 pi epsilon naught R times pi over 2 minus 1. All really complex stuff that we tried to do in the simplest possible manner. That's all I have for you on this video. Please feel free to like, comment, or subscribe, and we will continue our discussion with electrostatics next time.